I'll try to be more kinetic. Kinetic theory, what is it? It's trying to understand macroscopic properties on the basis of a microscopic picture, in particular, the jiggling around of molecules. That was on camera. Jiggle again later. So last time we talked about classical statistical mechanics. In fact, most of what we're going to say about kinetic theory will be classical. And in particular, we saw that in classical statistical mechanics, there is an equal partition principle. And what it says is there's a contribution to internal energy of 1/2 temperature associated with each a degree of freedom which is accessible, I'll say accessible quadratic degree of freedom. So quadratic means that it's a variable and the energy depends quadratically on that variable. Accessible means that the temperature is high enough so this degree of freedom is excited. And so we talked about the example of a diatomic molecule, which in addition to its center of mass motion, well, that's 3 degrees of freedom because the energy input in 3 dimensions depends on the 3 squares of components of momentum. Maybe I should say px, py, and pz squared for each one of the molecules in the gas. In addition, there is a vibrational degree of freedom, vibrating along the axis, and rotational degrees of freedom along 2 axes. The diagram's getting a little indecipherable, but think of it as a little stick, which has a non-zero moment of inertia for rotating about 2 different axes. And so if everything is accessible, the internal energy per particle would be 3/2 tau, or in other words, kT, associated with the center of mass motion, 3 quadratic variables for each molecule, px squared, py squared, or pz squared, and then plus another tau, because there are 2 rotational kinetic degrees of freedom, the kinetic energy of rotation about 2 different axes, or if you like, the angular momentum, L1 squared, L2 squared, about 2 different axes, another 2 quadratic degrees of freedom. And then there's another tau associated with vibration, because now we have a p squared and an x squared, since there's a restoring force for the vibrational degree of freedom. So p squared and x squared for vibration along the axis. So if everything's accessible, we have 7/2 tau for the energy per particle in the case of a diatomic molecule.
So why does px squared, py squared, and pz squared get 3/2, so the only other ones only get 1?
Well, everybody gets 1/2 tau.
Okay.
And so it's 3
okay, so it's 1/2 tau per degree of freedom.
Right. So this is 3 degrees of freedom, this is 2, and this is 2.
Okay.
Right. And so what does it mean to be accessible? When the temperature is sufficiently low as to be comparable to the level spacing for the quantum excitations, either rotational or vibrational, then quantum effects become important. So if kT, that is tau, is small compared to h bar squared over twice the moment of inertia, or h bar squared over I, then rotation spreads out, and similarly, when the temperature is small compared to h bar omega, as we discussed before, vibrations freeze out. For typical molecules, vibrations freeze out at a higher temperature than rotations. In classical statistical mechanics, we can also talk about the distribution of velocities for particles in a gas. As we discussed many times, if we count orbitals for a free particle, we have to consider, for in 3 dimensions, integrating over position and momentum, and there's a power of Planck's constant h, 2 pi h bar, associated with each dimension and the normalization factor. So if I integrate the position in the case of a free particle over the whole box, there's a factor of volume. So I can write that as volume, and then I can assume that we have a rotationally invariant distribution of momentum, integrate over the orientation of the momentum, and so I would integrate 4 pi t squared of the area of a shell momentum space dp divided by the normalization factor, 2 pi h cubed. Now, the people in the 19th century who were trying to understand statistical mechanics didn't know about h bar. But they did have the idea that when we count states, we should count a volume in the xt space. So they could write down a formula like this. They just didn't know how to normalize it. But for a lot of purposes, the normalization doesn't matter. In fact, if we're considering non-relativistic particles with momentum equal to mass times velocity, we can say there's some constant, and who knows what it is or cares, a factor of volume, and then the number of states per interval of velocity, or speed, really. V here is the magnitude of velocity, is weighted by v squared. That's coming from this p squared in the density of orbitals that we talked about before. So when we normalize it, the constant c drops out. I want to know what the probability distribution is for speed. You can say that the probability of speed is an interval. Now I'm going to have to talk even louder. Is an interval from v to v plus dv is p of v dv, and p of v dv is this v squared dv divided by a normalization factor, chosen so that when I integrate p of v dv over all speeds, I get 1. So the denominator is the integral of v squared, and then the Boltzmann factor. Here I'm counting the number of orbitals, but then Boltzmann and Maxwell also knew that the probability of an orbital being knocked, I didn't use this word, would be suppressed by a Boltzmann factor. So there's also a factor which goes like e to the kinetic energy divided by tau, and I should put that in the numerator as well. Okay. And so this integral, if we change to dimensionless variables, so I can write this as the integral 0 to infinity dx, x squared e to the minus x squared, by choosing x squared equals 1/2 mv squared tau. So in doing so, I multiplied by m over 2 tau, twice here and once here, and then I have to put in the compensating factor of m over 2 tau to the minus 3 halves. And this is just a number, which is, everybody knows, is the square root of pi over 4. And so when we divide by that factor, the conclusion is that the probability distribution for speed is the square root of 2 over pi, 3 powers of m over tau, e to the minus 1 half of the square root over tau. So that's called the Maxwell distribution of velocities. So what it means is that if we have, at temperature tau, an ideal gas, there it is, and then I randomly pick a particle in the gas and measure its speed, do that many times by sampling many particles, I will find them distributed according to the Maxwell distribution.
Didn't you miss a v squared? Didn't you miss a v squared?
I can't hear you.
V squared. Did you miss a v squared?
I sure did. Thank you. He asked me if I missed a v squared. I didn't. Now, if I have a container with a hole in it, and now I play the game a little bit differently, and each time a particle comes out through the hole, I grab it and measure its speed, then the distribution will be biased because faster particles come out at a higher rate per unit time, enhanced by a factor of v. So, question?
Why is the correct weight v?
Why is the correct weight v for the particles coming out?
Yeah, for the hole.
Because there's some... so the number of particles coming out per unit time is going to go like a density of particles times a factor of velocity. Okay? So it's going to be proportional to v times density. So think of this probability distribution as describing, if you can think of the density as being a density of particles in a certain speed window, and integrated dV. But the rate at which they're coming out per unit time will be enhanced by a factor of speed. Okay? So look at some little time interval. Take all the particles that came out, measure their speed.
Okay, so at least v has the right dimensions. You
Yeah.
need something, okay.
Yeah, but I mean, it's the rate. Faster particles are more likely to come out in a given time interval.
Yeah. But v squared would do the same thing.
What do you mean?
Well, I mean, if that makes faster particles.
I see. So why is it proportional to v? Well, I'm just saying that there's a flux. A flux is proportional to number per unit volume times speed. This is flux, meaning number of particles per area and time. So we have some hole of fixed area, right? And in each time interval, if I compare particles with two different speeds, right, with the same density, the particles which have higher speed will be coming out at a rate per unit time, which is enhanced by a factor of speed. Then if I look in one time interval at the particles that came out and I measure all their speeds, they'll have a distribution which is enhanced by an extra factor of speed. How should I say? P coming out of hole. So V dV will be proportional to VQ times the Boltzmann factor. sense?
I think
So if I do cut a hole out and let particles leak out for a while, Boltzmann distribution, which starts out quadratically as a function of E, then turns around. The particles that will escape will be biased towards the higher end of the distribution. So when the particles escape, then the mean value of the speed is going to be shifted down. Of course, if we just were to say, cut off the distribution and take away the high-speed particles, that's no longer a Boltzmann distribution because it's no longer in equilibrium. But if we wait a while, the particles, let's say I open the hole for a while, I let some of the high-speed particles escape, then I close the hole. After a while, because of collisions among the particles, they'll redistribute the energy and come back to equilibrium. Okay? But after they re-equilibrate or re-thermalize, the distribution will get shifted to the left. So the particles will be cooler than before. They'll still have Maxwell-Boltzmann distribution, but shifted to a smaller mean velocity, hence a smaller temperature. So that's an example of cooling by letting particles escape where the particles that escape are biased towards high speed. Just the way evaporative cooling works, like we talked about in the context of reaching ultra-cold temperatures for dilute atomic gases. Well, a story which I think you've seen before, but it's fun, so we'll just briefly revisit it, is how we understand pressure from the point of view of kinetic theory in an ideal gas. So we have gas in a box, and look at one of the walls of the box, and boxes don't usually have balls. They do have balls. And we consider the collisions of the molecules with one of the walls, and there will, if we have a density n of particles, let's say this is the z direction, and I'm looking at the wall which is normal to the z direction, then half the particles will be moving up and half will be moving down. So if I'm interested in the rate at which particles are bumping into the wall, I only consider the upward flux, which is means I'll consider half of the density of particles, and multiply that by the speed in the z direction to get the flux of upward moving particles. Again, by flux, I mean number per area and time. And each time a particle bumps into the wall and bounces off elastically, it will give an impulse to the wall, which is twice its z component of momentum. So that impulse, since it has upward momentum, mvz in the z direction before the collision, downward momentum, mvz after the collision, the change in momentum is 2 mvz. And so the pressure which is the average force per unit area, I obtain as the impulse or change in momentum per collision times the rate at which collisions are occurring, number of collisions, divided by area and time. So the force is the impulse absorbed by the wall per unit time. So this is the pressure. And so I can write the pressure as an average over the distribution of speeds in the gas of the density, because that goes into flux, times the mean value of m bc squared, because I have a 2 m bc in the impulse and a 1/2 n bc in the upward flux. So in other words, it's number of particles per unit volume. I'll put in a factor of 2. And then this is the kinetic energy coming from motion in the z direction. Equal partition tells me that classically this is a quadratic degree of freedom. This is the kinetic energy due to that degree of freedom, so that's 1/2 tau. So this is n tau over v. That's the ideal gas law as interpreted from a microscopic point of view in kinetic theory arising from molecular collisions. What we'd like to do is understand the departures from ideal behavior, which we haven't talked about very much in this course, coming from the fact that the molecules actually do collide with one another and the gas is not ideal. So, we're going to take a very naive point of view, but which will be good for understanding things qualitatively and for order of magnitude calculations, which is to think of each one of the molecules as a billiard ball, which can collide elastically with other billiard balls, and with some finite size. Now, the size of the molecules is going to be important. Maybe stupidly, I call the radius of the billiard ball d, which sounds a lot like the diameter, but d for distance. So let d be the radius of one of the billiard balls. And now let's consider one of these billiard balls moving along, sweeping out a cylinder over time. And every once in a while, there will be another billiard ball. Not necessarily with its velocity oriented to collide head-on, but such that there's a collision. And when the collisions occur, what I really should do is average over the impact parameters of the collisions. But we'll consider a collision to just be something that randomizes the direction of speed, another crude approximation. And so, think of this cylinder being swept out by the moving billiard ball. But every once in a while, the billiard ball forgets what its previous direction of motion is and heads off in a new direction. Okay? So it moves for a while, and then there's a collision, then it moves off in a new direction, and then there's another collision, and then a new direction again, and so on. Now, how often do collisions occur? It's determined by two things. One is the size of the particles, and the other is the typical separation between particles, or the density of particles. We can think about it this way. If the molecule moves distance L, this cylinder that it sweeps out has a volume which is its cross-sectional area, which is just pi d squared, times the distance L that it travels. And how often is the particle going to bump into other particles? Well, if it moves a distance L, the volume per particle total total volume available divided by the number of particles is 1 over the concentration by definition. So the number of collisions is going to be the typical number of particles contained in the volume occupied by this cylinder. Okay. So we'll say the number of collisions is the swept volume of the cylinder divided by the volume per particle so that will be dividing by volume per particle means multiplying by n, so just n pi d squared L. And we'll call the mean free path the typical distance that the particle travels before a collision occurs. So when the number of collisions is 1, that means the particle has moved distance L given by the mean free path. So mean free path, M at P, mean free path, equals distance traveled between collisions is L mean free path. I get just by setting the number of collisions to 1. So 1 over concentration times pi d squared. So typically, how big are molecules? How big are molecules?
A few angstroms?
Yeah, let's say a few angstroms. And what's the concentration of an ideal gas at standard temperature and pressure?
22.4 moles per liter.
All right, that was quick. So if we consider ideal gas, and let's say it's 0 degrees Celsius and 1 atmosphere, then the concentration, translating what you just said, is something like 2.7 times 10 to the 19 particles per cubic centimeter. And so what we find for the mean free path well, it's something like 10 to the minus 5 centimeters. So it's larger than the size of the molecules by a factor of maybe a few hundred or so. And it's larger than the mean distance between molecules. In fact, I'm not worrying about factors like pi and stuff. The mean free path goes like the typical separation between molecules cubed, because that's just another expression for the volume per particle or volume density, and then divided by what I call d squared, the typical cross-sectional area of the molecule. So if we compare the mean free path to, this means typical distance between molecules, then that goes like the separation divided by the size of the molecule squared. So typically the separation is large compared to the size of the molecule, and then the mean free path is larger still. So when we speak about transport phenomena in physical systems, we usually have in mind is the behavior of the system over distance scales which are large compared to the mean free path. So on that scale, if we were following the motion of a particular molecule, it would get scattered many times, having its motion randomized typically over some characteristic distance scale, and its trajectory would look just like that. So we call this the diffusive regime, or the behavior of a molecule which is scattered many times and walks around in random directions is called diffusion. And it's important because it arises in many different physical contexts. I'll mention a few. We can consider the diffusion of energy in, let's say, a gas where the temperature is not uniform. So in some regions of the system, the molecules have higher temperature. In other regions, lower temperature. What happens? Well, the energy diffuses. The higher energy particles scattering many times. Eventually, the energy that they carry gets spread out until the system rethermalizes. So diffusion of energy that's what we call thermal conductivity. It tells us how quickly high temperature moves towards low temperature in the system. When we consider diffusion of electrical charge, that's electrical conductivity. It tells us how quickly electric charge will flow from a region of high electric potential to low electric potential, with the electrons being scattered many times along the way. Diffusion of momentum in a fluid governs what we call viscosity, or resistance to flow in the fluid. Now, all these things are diffusive processes. For all of them, it's important that we're talking about a scale which is large compared to the mean free path when microscopically particles are scattering many times. Another context in which diffusion arises is mixing. Here's an example of mixing. The blackboard is water, and I put a little drop of ink in the water, and then I come back a minute later, and the ink is starting to spread out. So So it looks less blue than before, and the region which is colored is bigger. And then I come back 2 minutes later, and it's spread out even more. Why is that happening? It's because the ink consists of many molecules. They're being repeatedly scattered by water molecules, and that's causing the distribution of the ink molecules to gradually spread, giving rise to mixing. After a long time, the ink will be uniformly distributed in the chamber of water. Well, I've done many experiments with ink drops over the years, watching how fast they spread. And I've been able to reproduce something called Fick's law of diffusion, and analyzing my data. So it's something that's empirically observed to be true, and what it says is, if I consider the flux in case of ink, the flux of ink molecules, what's the net rate if I put down a surface somewhere in the water at which the ink molecules per unit area and time are flowing across that surface? That's equal to, well, it's proportional to the gradient of the density. With a minus sign and a constant, which I'll call capital D. So, in the case of the ink, I started out with a high concentration of ink, right in the center. Near the edge of the droplet, there's a big gradient in the ink density, and that makes the ink then spread out. And this is how it spreads out. And D is called the diffusion constant, or sometimes it's called the diffusivity. Another way of writing this law of diffusion is to make use of the continuity equation. The ink molecules are conserved. There's some fixed number of ink molecules floating around in water. So if I consider some little cell or volume in the water, there it is, and then there are two things I can equate. One is the total flux of ink through the walls integrated over the boundary of the cell. So that's the total flux out in the number of ink molecules per unit of time. That's equal to obtained by integrating the flux over the boundary of the cell. And I can use the divergence theorem to write that as an integral over the volume of the divergence flux. And another expression for the rate at which the ink molecules are leaving the cell is, well, I consider the density of ink molecules per unit volume integrated over the volume. So that's the total number of ink molecules in the cell, and this is the rate at which that's increasing. So I can write that as the integral of a minus the partial derivative of the density per unit time. So since I can equate these two, there's a continuity equation satisfied by ink molecules. ddt, density of ink molecules, is equal to minus the divergence of the flux, but according to Fick, the flux can be written as minus d times the gradient of the density. So this becomes d times gradient squared of density. So our conclusion is that the density of each molecule obeys the partial differential equation. I consider n as a function of time and position. It satisfies d dt n equals d gradient squared n, which is called the diffusion equation. So what we'd like to do is understand that equation from a microscopic point of view, how it arises from molecular collisions. Does anybody know who was the first to explain the diffusion equation from a microscopic point of view?
Einstein?
Yes, it was Einstein. What year?
1905.
It was 1905. It was a good year. And what Einstein realized is that we could understand diffusion by thinking of molecules making random walks, like this picture, that each one of the ink molecules actually is walking around, each time turning in a random direction. So each ink molecule has no preference between going one way or another way. It kind of moves in an isotropic way. But if we have a gradient where there are more ink molecules over on the left than there are on the right, then if I look at some particular cut of the system into two parts, we'll have more ink molecules flowing from left to right than from right to left, if there are more ink molecules over on the left side of the cut. And that will cause the distribution to smooth out, or the gradient to go down, and that's what the diffusion equation describes. Yeah.
So the smoothing is not due to interactions?
It's not. It's due to collisions.
Okay.
It's due to collisions, but microscopically, each ink molecule doesn't care whether it goes left or right.
Okay.
It's as likely to go left as right.
But there are more.
But there are more on the left, and therefore there are more going from left to right than right to left across the cut. And so, if I have some initial distribution of ink molecules, let's say it looks like a Gaussian, what's going to happen? It's going to spread out. And that's what the diffusion equation describes. So, I want to have kind of a simple model in which we can see that how that flow from high density to low density results from decisions that are made by individual molecules at the single molecule level. So I'll consider this kind of oversimplified model, but it illustrates the point very nicely. And I'll stick with one dimension to start with, since that's the easiest thing to discuss mathematically. So I've got a one-dimensional gas, but it's not an ideal gas. The particles are colliding. But think of any particular particle. Let's try to follow what it does. And let's imagine, although the system might really be continuous, making it discrete for purposes of analysis. So I'm going to consider a particle which lives on a lattice, lives on a set of discrete points. And there will be some time step, which I'll call epsilon, and a lattice spacing, which I'll call delta. So delta is the spatial distance between these lattice sites. And the time step epsilon, well, every time epsilon, the particle is going to decide to either hop from its current position to the side on the left or the side on the right. So it always hops. It always hops by one lattice spacing, but it's indifferent about whether it hops to the left or to the right. Okay? So in each time step, the particle flips a coin to decide what to do. It moves to a neighboring site. And it goes to the left with probability 1/2, and to the right with probability 1/2. And so if I imagine there's some probability distribution to begin with, describing where the particle is at a particular time, in each step that probability distribution will change, it'll evolve. And then we'd like to consider over many time steps how the probability distribution changes. And we'll see that if we imagine taking a formal limit in which the lattice spacing goes to 0 and the time step goes to 0, we get the diffusion equation. Let's see how that works. Well, in fact, you kind of recognize the model, all right? It's from the first lecture, but I've changed the names to protect the innocent. Suppose we start. I'm going to consider the position, in other words, to be s times delta. Delta is the lattice spacing, s is an integer, and the time t is equal to, I'll call it n, I guess. I may regret that since it doesn't count the same thing as the density, but that's what I have in the notes, so we'll stick with it. Where n is an integer. So n goes to n plus 1, that means we go from a time step to the next time step. And when s goes to s plus 1, that means the particle moves to the side on the right. When s goes to s minus 1, it moves to the side on its left, right? So after n time steps, well, let me say it. Suppose we start at time 0, or n equals 0, with a particle at s equals 0 at the origin. And I mean that's true with probability 1. Now, what's the probability distribution going to look like after many steps? Well, what's s going to be? It's the number of steps that we make to the right minus the number we make to the left. That's where we wind up. Okay. Each time we either go left or right. And the total number of steps to the right we've made is n right minus n left. It can be either positive or negative, depending on whether I wound up to the right of the origin or go left of the origin. The total time is just the total number, or the discrete time, is the total number of steps. Some of them I went to the right, and some of them I went to the left. So this is just like tossing a coin n times and asking what's the excess of heads over heads. It's a calculation we've done. When we consider many tosses, so many time steps, and then we have Gaussian. And from the analysis we did, flipping a coin many times back in the first week of the class, the probability distribution for S after n flips, or n time steps, is 1 over the square root of 2 pi n e to the minus s squared over 2n. Using the Stirling approximation, which we can justify when n is large. And so I can think of that as a probability density on the line question.
You just doing the random walk, right?
I'm just doing a random walk, right? It's unbiased. So I go with probability 1/2 to the left or to the right. So I could also describe this as a probability density on the line. Which I'll call P of x and t. I put in a factor of 1 over delta. E to the minus s squared over 2n. 1 over delta, because now it's a probability density, and if I want to know the probability that the particle is found in some interval which has length delta times an integer, I multiply this probability distribution by the length of the second. And then I can put this in terms of, since the time is an epsilon and the position is s delta, I can write this as 1 over the square root of 2 pi delta squared. That's just putting this delta inside the square root, and then write n as time over epsilon. So delta squared over epsilon times time, and then in the exponential, I have e to the minus epsilon over 2 delta squared x squared over t. Again, just writing s as x over delta and n as t over epsilon. So I'd like to convince you that we can get this same formula in a different way by writing down a microscopic equation that describes the evolution of the probability distribution and then solving that equation. And I'll get our differential equation, which will be the diffusion equation, by starting out with a difference equation using this discrete model, and then take a limit in which the time step becomes small and the lattice spacing becomes small. And the difference equation looks like this. It's a difference equation for the probability distribution, which depends on the integer valued time, the number of time steps, and the integer valued position, the number of lattice spacings to the right when s is positive, to the left when s is negative. And the observation we make is this, that if we want to know what the probability is, how can you be at site s at time n? Well, if you're at site s at time n, where were you at time n minus 1? Here's site s. Site s plus 1, s minus 1, etc. In each step, you either move to the left or to the right. Okay? So, if you're at site s at time n, then at time n minus 1, you had to either be at s plus 1 and to have taken a step to the left, or at site s minus 1 and taken a step to the right. Okay? Those two things are equally probable. So in other words, the probability that you wind up at site s with at time n is 1/2 the probability that you jump to the right times the probability that you were at site s minus 1 at time n minus 1. Plus 1/2 the probability that you were at s plus 1 at n minus 1. Because if you were at s plus 1 at time n minus 1, then with probability 1/2, you jump to the left and you wound up here. And if you were at s minus 1 at time n minus 1, with probability 1/2, you jump to the right and wound up at s. Okay, everybody believe that equation? So, I'd like to write an equation for how the probability of being at s changed between time step n minus 1 and time step n. So I'll subtract that away from both sides. The amount by which the probability of being at site s increased between time step n minus 1 and time step n is 1/2. Probability of being at, I'll write what I had before, s minus 1, n minus 1. But then I subtract this away and I'm factoring out a 1/2, so I'll put in a 2, minus 2, probability of being at s, at time n minus 1, then plus probability of being at s plus 1 at time n minus 1, multiplied by 1/2. And you can't prevent me from saying it's the same thing as 1/2 times the probability of being at s plus 1 at time n minus 1 minus the probability of being at s at time n minus 1 minus the probability of being at s at time n minus 1 minus the probability of being at s minus 1 at time n minus 1 in parentheses. Yeah.
In your probability of xt, why do you divide it by a delta?
Why did I divide by delta here?
Yes.
That's because this is the probability density. By that I mean that the probability of being between x and x plus dx,
I see.
right, is the probability of x dx, but changing the integer by the amount, changing the distance by delta times that amount, so I had to divide by delta. Okay, so now I want to take a, so to speak, continuum limit. In other words, I want to imagine that the probability distribution changes very smoothly when I change the lattice spacing. So the characteristic scale over which the probability distribution is changing is many lattice spacings. And the probability distribution is changing just a little bit in each time step, because I've chosen the time step to be very short. Okay. So, if P of xt is smooth on scale, I guess I'll say delta x border delta and delta t border epsilon, then we can approximate difference equation by the differential equation. That is, I will think of this difference as being the elapsed time in one time step, which is epsilon, times the derivative of the probability distribution at site S, or at some particular position x, with respect to time. So the left-hand side becomes the partial derivative of the probability distribution with respect to time times the time step epsilon. And I guess strictly speaking, I can say it's evaluated at position S on the lattice and a time in between time epsilon n and time epsilon n minus 1. I'm taking I consider the time at which this derivative is defined as the midpoint of the interval. And what I have on the right-hand side, I can think of as the lattice spacing delta times the partial derivative of the probability distribution with respect to x. That's this difference between probability at time s plus 1 and probability at site s plus 1 and probability at site s. Think of that as the difference delta times the spatial derivative evaluated at the midpoint. So that's delta times partial derivative of p with respect to x evaluated at position s plus 1/2 time n minus 1. But then I have minus delta partial derivative of p with respect to x evaluated now at s minus 1/2 time n minus 1. That's in the second term. I'm subtracting the probability at site s minus the probability at site s minus 1. So this is the first derivative of the probability distribution. I'm taking the difference between two positions which are one lattice spacing apart. So we can think of this as another factor of delta times the second derivative of the probability distribution with respect to position. And now evaluated at the midpoint of this interval, which is s, and time n minus 1. So up to higher order corrections which have to do with the fact that here I have time n minus 1/2 and here I have time n minus 1, which I'll be able to ignore when I take the limit of epsilon going to 0. We have that the probability distribution in this smooth limit satisfies the differential equation. Derivative of probability density with respect to time equals delta squared over epsilon, if I divide both sides by epsilon, times 1/2, I'll put a 2 in the denominator, second derivative of p with respect to position. So that looks just like the diffusion equation if I identify delta squared over 2 epsilon as the diffusivity, the diffusion constant.
What's the 1/2 there?
Well, the 1/2 came
From
from here and here, but I had it here, but I missed it there. Okay. It's the 1/2 because of the 1/2 in the expression on the board all the way over to the right, but I don't want to drive the cameraman crazy and walk over there again. So you can just back up the video and see what happened. Okay. And so d is equal to delta squared over 2 epsilon. Of course, if I talk about the density instead of the probability, it's just, they just differ by a constant factor. So the density obeys the same differential equation as the probability distribution, namely the diffusion equation. And actually, we can consider the case now in the continuum language that we considered here, where we started out at the origin. We can ask, what is the solution to the diffusion equation if the probability density at time 0 is just a delta function. So I've normalized it as I'm supposed to, so that the integral p of x dx is equal to 1. So if there's any justice, if it's really to be interpreted as a differential equation governing a probability distribution, it will be non-negative. Its probabilities should be normalized at all times. Well, if we look at the expression we had just by thinking about the unbiased coin for the probability density as a function of position and time, written in terms of what we've now identified as the diffusivity, delta squared over 2 epsilon, at time t, the solution with this boundary condition, when we start out at the origin, can be written as 1 over the square root of 4 pi dt e to the minus x squared over 4 dt. And you can check just by differentiating with respect to x twice and differentiating with respect to t once that that expression obeys the diffusion equation. It's the unique solution obeying our boundary condition that the probability distribution is a delta function at time 0, and it is normalized correctly at all times and always non-negative. So we can check that p of xt is non-negative, and that the integral at all times is 1. So what happens to our delta function is that it spreads out. That's the distribution at time 0. And then at a later time, it's a broader Gaussian. And at a still later time, even broader Gaussian. How broad is it? The variance of this probability distribution tells us how broad it is. Namely, the mean square value of x is given by the variance of this Gaussian, and that's just 2dt, where t is the diffusion constant, which we now know in terms of our lattice model we can write as delta squared over epsilon times time t. So the width of the distribution grows like the square root of t. The square root of the mean square value of x squared is equal to the square root of 2 dt. In terms of our naive microscopic model, we can think about it this way. Think of each time step as the time the particle travels a mean-free path and then gets its position randomized. So after it moves distance delta, it forgets what direction it was moving and moves off in a random direction, either left or right with probability 1/2. So you can think of delta as being like a mean-free path. How fast are the particles moving? Well, they hop either to the left or the right, a distance delta in time epsilon. So speed is delta over epsilon. So, at least in our naive model, we can think of the diffusion constant from the point of view of a microscopic theory of our molecular gas as a factor of 1/2, which you shouldn't take too seriously because it kind of depends on the crude model that I've chosen. But what is of broader interest is we can think of it as a mean-free path times the speed. The mean free path is how far you travel before you forget what your initial direction of motion is. V is how fast you travel. The product of the two is essentially the diffusion constant, which tells you how quickly the probability distribution spreads. So the formal limit that we took to get a diffusion equation is the limit in which I call it the delta goes to zero limit. The diffusion equation applies for a delta goes to zero and epsilon goes to zero, but what we hold fixed is V, which is delta squared over 2 epsilon. So saying delta goes to zero, well, that means we're observing the behavior of this fluid on a characteristic distance scale which is large compared to the mean free path. And over time scales which are long compared to the typical collision time, epsilon. Now something that's kind of weird about this is that when we take this formal limit, the speed, delta over epsilon, is behaving like the diffusion constant, which we're holding fixed, divided by delta. So the speed is actually going to infinity. Well, another way of saying it, maybe a better way of saying it, is that if we look at x as a function of t, in our lattice model, x is hopping back and forth. We start out at the origin, maybe we go up, down, down, up, down, down, up, down, and so on, kind of at random. And now we want to consider the behavior of that curve when we take the time interval between jumps going to zero. And what happens as delta epsilon go to zero is that x of t is continuous, but with no derivative at any point. No first derivative. At any value of t. So another way of saying that is if you think of this x as a function of t as being governed by some trajectory, some function of time, x, the square root of x squared, is increasing like the square root of t. So that is smooth as t goes to zero, but its first derivative is blowing up as t goes to zero. So if you look with a microscope at a diffusing particle with better and better resolution, it's always wiggling. You can't take a limit in which the resolution gets arbitrarily fine and becomes smooth. Now, of course, that's kind of an artifact of the fact that we've taken this limit of delta going to zero. In practice, there really is some cutoff, which is given by the mean free path and the collision time. So if you finally look with good enough spatial resolution and time resolution so that you can see individual collisions, then you see the particle has a trajectory and it's differentiable except for the discontinuous change in the direction of the velocity at each collision. Of course, we can also generalize to more dimensions. And in fact, in 3 dimensions, it's really the same thing. So from the point of view of the lattice model, you can think about a 3-dimensional lattice. Let's say it's a cubic lattice in 3 dimensions. So each position on the lattice has 6 neighbors now. In fact, if it's d dimensions, cubic or hypercubic lattice, each site has 2d neighbors. That's because there are d dimensions, d lines along which you can move, and for each of them you can either move up or back. 2 possibilities along each axis. So if we do the same analysis that we've already done, it's exactly the same thing. Except now we'll say, in each time step, the probability for each of 2d possible directions is 1 over 2d. In other words, it's a uniform distribution. There are 2d possible ways you can go, and they're all equally probable. Before we had 2 ways, and the probability was 1/2. So in 3 dimensions, there are 6 possible ways to move, up or down, left or right, forward or back, and each gives the probability 1/6. So we will again get a diffusion equation. The probability distribution will obey the differential equation if we take the same formal continuum limit, delta and epsilon going to 0 as before. The time derivative of the probability is diffusion equation times gradient squared p, because I'll have different first derivatives like this for each one of the 3 directions, x, y, and z. And where the diffusion constant now will be delta squared over, in d dimensions, 2d times epsilon instead of 2 epsilon in the denominator. That's just coming from the probability of being 1 over 2d instead of 1/2 for each of the ways you can go. So in particular, in 3 dimensions, we will take d, 2d delta squared over 6 epsilon. So if you want to think of that as expressed in terms of a mean free path and a time, or in terms of a mean free path and a speed, we would say the diffusion constant is 1/6 times delta over epsilon, or 1/6 a mean free path times speed. And actually in the book they write down a similar formula but with a 1/3 instead of a 1/6, but don't worry about it. We're both using kind of crude models and they're slightly different. The important thing is that the diffusion constant, like we found in the one-dimensional model, scales like a mean free path times the speed of the molecules. And that determines how quickly probability distributions spread out. So if you probably the easiest way to think about it is if you have three-dimensional diffusion, the particle is independently doing a random walk in the x, y, and z directions, each one of which we can think of as described by flipping an unbiased coin many times. So the distribution that we get after a long time, if we start out at the origin, is just going to be the product of the one-dimensional distribution that we found in our earlier calculation for the x, y, and z directions. So in other words, if at t equals 0, we have a delta function normalized to 1 and would support at the origin, then at time t, the probability distribution will be 1 over 4 pi t to the 3 halves e to the minus x squared over 4dt. So that's just the product of the probability distribution I wrote down earlier for the x direction, the y direction, and the z direction. So I get x squared plus y squared plus z squared here, or in other words, the total distance traveled squared. And again, you can check just by plugging in to this form of the diffusion equation that in 3 dimensions, this is a solution. And as in 1 dimension, the distance that our particle travels in time t goes like the square root of t when t is small. So you can think of the path if we regard the diffusion equation as describing the probability distribution for a diffusing particle as one which is continuous but not differentiable at any point. The particle keeps changing its mind about what direction it's moving in. So Einstein did another great thing in this 1905 paper, which was his third best paper here. And that was he derived the so-called Einstein relation. A relation between the diffusion constant and something called the mobility involving temperature. The mobility is a statement about when a particle is diffusing through a medium and we apply a force to it, at what point it reaches terminal velocity. So in other words, if we apply a force, the terminal velocity in the presence of that force is proportional to m, and the constant of proportionality is called the mobility. So this is terminal speed, or terminal velocity. This is an applied force. Like, say, gravity trying to pull an object through the fluid, and this is the mobility. So it's kind of a remarkable equation, because the statement about mobility, this definition of mobility characterizes dissipation. It's the resistance, the friction that a particle encounters when it flows through the fluid. The diffusion constant, though, has to do with fluctuations, the way a distribution spreads out. And we'll see next time why the two are related. Okay.